Welcome everybody, this is the Crystal Clear Electronics video series 8th chapter. In this chapter, two different parts will show you what the Astable circuit is. Our presenter today is Vincze. Can you share some things about yourself?
Thank you very much for the introduction, Adam. I'm Vincze, a qualified electrical engineer and one of the authors of Crystal Clear Electronics. I'm currently working as a project manager in a medical device development company, but when time permits, I'm also returning to electronics design. The Astable circuits on this presentation are almost as old as our grandparents, but they are the rock stars of electronics and are still in use today. Adam, before we begin, can you also please tell us a little bit about yourself?
Of course. I'm Astable, a certified mechatronics engineer, co-author and editor of the Crystal Clear Electronics written materials. Since I was in high school, I have been involved in teaching and self-development, which is why I have been involved in the creation of the Crystal Clear Electronics textbooks from the very beginning. The 8th chapter was written by Szabolcs. But before we get started, here's some important information. If you ever get stuck, feel free to pause the video and rewind it. But most importantly, if possible, try out each example for yourself. If any of the circuits don't work, ask your teachers or friends. Now, let's get started with this evergreen electronics topic.
Thank you, Adam. The fact that it's an evergreen LED flicker circuit solution also means that it comes across to us where we wouldn't think it would, for example, on the Christmas tree.
What does the word Astable means and why does it go on the Christmas tree? Let's examine the tasks and hopefully everything will be crystal clear and you get a stable knowledge.
First, build a 5-volt power supply with the previously known 7805 voltage regulator. Then, build the Astable circuit on the breadboard based on the circuit diagram shown in figure 1. Connect 5-volt voltage to the circuit using the constructed power supply. You'll notice that the two LEDs are blinking alternately, approximately with a period of 0.5 to 1 second. Don't forget, before changing a circuit on the breadboard, always turn off the power supply. First, replace the R1 resistor with 33 kilo-ohms. After the power is turned back on, the LEDs are blinking asymmetrically. The D2 LED will light for a shorter time than the other. The same happens with LED D1 when you replace R2 while R1 is 100 kilo-ohms. If you replace both resistors with 33 kilo-ohms, then the blinking will be symmetrical again, but it will be about 3 times as fast as it was with the 100 kilo-ohm resistor. From this, we can draw a conclusion that the blinking frequency is related to the value of R1 and R2.
It's really blinking faster.
Now let's continue experimenting. Replace C1 with a 22 microfarad capacitor. Blinking is asymmetric again. Now the D2 LED lights up for a longer time. You can experience the same with the D1 LED when you replace C2 with a 22 microfarad capacitor. If you replace both C1 and C2 with 22 microfarads, the blinking will be symmetrical and about half as fast as before. So the blinking frequency also depends on the capacity values. If you try to replace R3 and R4 resistors, for example with 1 kilo-ohm, the blinking frequency will not change, but the brightness of the LEDs will be different. Try strictly with higher values, because a lower value than 220 ohms can damage the transistor and the LED. We dove into changing components and the lights are already flickering like in a disco.
So far this is fine, but we have not learned anything about the reasons why. It seems that the values of R1, R2, C1 and C2 determine the frequency of the flashes.
To understand exactly how it works, we need to delve a little into the spiritual world of our connection. Let's get started. Let's start with the case that the transistor T1 is in conducting state, D1 is lighting, and T2 is closed, D2 is not lighting. Then, the voltage on the T1 collector is nearly zero. In the first half of the entire cycle, C2 is charged via R2, the voltage measured on the capacitor slowly increases, and the voltage of the right arm in the figure reaches T2's forward voltage, which is about 0.7 volts. At this moment, T2 transistor opens, its collector voltage will be 0, so D2 lights up. Practically at the same time, D1 turns off. But why? To understand, you first need to know that the voltage between the capacitor's arms cannot change instantaneously. Therefore, at the moment of switching, the voltage before switching can be measured on capacitor C1. Figure 4 shows the voltages before the switching happened. At the right side of C1, the voltage is the supply voltage minus the LED forward voltage, and on the left arm, it has 0.7 volts because T1 is open. The voltage measured on the capacitor should be the difference of these two voltages. Since the sum of all the voltages is 0, so UBE1 plus UC1 minus UCE2 equals 0, it follows that the capacitor can measure 2.8 volts in the marked direction. At the moment of switching T2, the voltage of the capacitor remains the same, but the collector voltage of T2 decreases to 0. Based on Kirchhoff's voltage law, UBE1 plus UC1 minus UCE2 equals 0. The base emitter voltage of transistor T1 is minus 2.8 volts, which is less than its forward voltage. For this reason, T1 turns off and no more current flows through D1. That's why D1 turned off when D2 lit up. So right now, D2 is on while D1 is not. In the second half of the entire cycle, R1 will charge C1, which means that the voltage of the base emitter of T1 will increase up to 0.7 volts. At this point, the T1 transistor conducts. D1 is on. The capacitor C2 retains its pre-change voltage, which results that the base emitter voltage of T2 will be minus 2.8 volts. This will turn off T2 and D2 will be off. From there, the process is repeated. The principle of operation can also be checked by measurement. Replace R1 and R2 with 1 megaohm resistors, C1 and C2 for 22 microfarad capacitors, and then turn on the voltage on the circuit. The replacement of the components was necessary to keep the blinking speed much slower, so you can follow the change of voltage on your meter. Touch the COM wire of the multimeter to the ground of the circuit, the positive wire to the base of one of the transistors, and observe how the base voltage changes. When the LED in the collector circle of the transistor extinguishes, the voltage will be negative, about the difference of the supply voltage and the LED opening voltage, and then slowly grows up to about 0.7 volts, then the LED will light up. This complies exactly with the principle of operation of the circuit. During the measurement, the period of blinking may change. This can occur if the so-called internal resistance of the multimeter you use is comparable to the size of the resistors used in the circuit. You don't have to worry about this phenomenon for the time being, so you can pay attention to the change in voltage. It can be seen that the turn-on time and switch-off time for T1 and T2 are set by the time required to charge the capacitors C1 and C2, which in this case are defined by the values of the components R1 C1 and R2 C2. It can be deduced that the required charging time is the value of the resistor times the value of the capacitor times a constant, which in our case results in 0.69 seconds. You also saw the LEDs blinking at a slightly smaller interval than a second. It's also clear from the formula that if you reduce the value of the resistance, the time when the transistor is on will be reduced. This is the time when the LED is on, which corresponds to your experience. It can also be read that if you increase the capacitor's capacity value, this time will increase, i.e. the blinking will slow down. You could also experience this when we replace the capacitors. During the experiment, before understanding the operation, you have already discovered how to change the blinking time. By understanding the operation, you can exactly predict how much blinking time is expected. The meaning of the word stability refers to permanency, constancy, and A is an alpha privative, that is, the meaning of the word astable is not permanent, variable. In this circuit, the state of the transistors was not constant, they were turning on and off. The measurable voltage at the collectors was either 0 volts or close to the supply voltage. The voltage, which is changing between these two values, is called a square wave. Now we have looked at how to implement an astable circuit with transistors. We have done a lot of interesting experiments and answered a lot of exciting questions, but I have one more. What do you have in mind that makes the flashing begin?
Since the components of the circuit, i.e. resistors, capacitors, transistors, are not perfectly uniform, once our circuit gets the power supply, one transistor will turn on sooner than the other, starting this oscillation, i.e. blinking.
Thank you, Adam, for the explanation.
You're welcome. This shall be the end of the video. Thank you for watching us. We hope we will meet you in the next episode. Goodbye.
Bye!